Continuing our discussion for the CMOS power, and as we said last time, that the CMOS um, um, power can be divided or classified, I should say, to dynamic and static. We said that the dynamic power um, is dissipated due to switching power, and we define this as the power needed to charge and discharge the output of the transistor, the capacitance right here. While switching power, I'm sorry, well, the second type is the short circuit power, which is basically the power caused by the temporary state of PMOS and NMOS being on. Now, somebody might say, here's a question. Um, the CMOS device is supposed to have either the PMOS on or the NMOS on. How come they both are on at the same time, causing the short circuit? Well, the answer for that is this, that the short circuit really happened temporarily for a very short time when both the NMOS and PMOS are on as they transition between the on and the off state. They don't stay on both of them for a long time. They just happen to overlap in the on state for a very short time and causing short circuit. That's why last lecture we said we are going to ignore this because it is really not going to be of that big of magnitude, and we will attribute most of the dynamic power to the switching power. Okay, now the static, we'll cover it later on, and we said that in terms of the switching power, okay, so we said the switching power, and we can say loosely that this is the dynamic power, and knowing, by the way, that dynamic includes switching plus short circuit, but since we are ignoring short circuit, so we'll say loosely that the dynamic power equal short circuit. I'm sorry, the dynamic power equal the switching power. Now, we say that this is equal to um, alpha times um, C times V square times frequency. And today we are going to discuss how to lower or reduce power consumption. And obviously, this is a really a big topic. Um, low power low power designs and low power and low energy designs are of a great interest in the research area as well as in consumer electronics because everybody is going mobile, um, sensors, and we would like to conserve energy as much and power as much as we can. So we want to conserve energy and reduce power of the switching devices. So how do you do that? Well, the answer is right here. You reduce this, or you reduce this, or you reduce this, or you reduce this. So today's topic, we're going to talk about the how you reduce the activity alpha, the capacitance, the voltage, and the frequency to do what? Well, to lower the uh, power consumption. Okay, so let's go back to the slides here. And um, so we talked about all of these. Sorry, I should have probably started at the where we stopped last time. But anyway, we're gonna flip those went. So this is how we're gonna reduce the power. It is we are going to reduce the power by reducing the activity factor alpha, the capacitance C, voltage supply V, and frequency F. And the approach typically attacks all of them, not one specifically. And this is where you get the most advantage. As we said, I'm going to repeat this one more time. Dynamic power equals switching power plus short circuit power. We are ignoring this for the purpose of these lectures, and that's why you see us talking about typically dynamic power almost equals switching power to certain extents. Uh, Other people might disagree, but for the purpose of these lectures, we're gonna assume that. Okay, all right. So let's talk about the activity factor, which is alpha. Alpha is defined as, well, first of all, we have to, if I may go back to my drawings. Um, uh, let's see. Here's my. Um, uh, all right. Okay. All right. So what we have here is, let's see. What we have here is that typically a signal. Let's say, for example, you have a gate here, a NAND gate, and there are inputs A and B and C. And that's just output F, for example. Okay, so this is A NAND B. What we are trying to discuss here is that how can we estimate the activity of this output signal given the probability of the input signals? Okay, what? The activity of an output signal given the probability of the input signal. So we would like to calculate the activity of signal output F given the probability of A and the probability of B. That's what we're trying to achieve here. Okay. Now, what happened is that, first of all, here's a definition that says the activity of any signal is defined as the probability of the signal switching 1 times the probability of the signal switching to 0. Okay, so that's just a matter of definition. Um, okay. Now, typically, or you could say that it is the probability of 1 times the probability of 1 inversion, because we are assuming that a signal can be either a 0 or a 1. Now, keep in mind, we do understand that there are some signals that take more than just one state, could take 0, 1, or high impedance. We are not discussing those yet. We're going to limit ourselves to signals with binary values of 0 or 1. Okay, at any case, so okay, so this is really this is really and probability of a signal being a 0 equals the inversion of probability of 1, and which is equal 1 minus the probability of 1. Well, um, what that means is that alpha here then equals, um, it is equal the probability of 1 times 1 minus the probability of 1. For the sake of abbreviation, we're not going to say probability of 1. We'll just say that probability. That is very obvious that it is a probability of 1. Okay, so then what does that mean? Well, what it means is that if we have a plot where we have a signal, uh, which has a probability of switching to a 1, okay, and here is alpha, um, and the problem, we're going to assume that the signal, let's just pick another color here. Okay, so we're going to assume that the signal has from 0 all the way to 50%, okay, switching. Now, keep in mind, in some cases, your textbook assumes that the signal can switch up to a maximum of 50%. Sometimes a signal can change, the probability of the signal can change more than that, but we'll stick with textbook here. So if you compute alpha here, then you'll see a nice curve that goes all the way up to 0.25, and then it drops down to like so, and the maximum value here is 0.25. Okay, so what does that mean? It means a signal with an activity of 0.25 occurs at a maximum point when the probability is 0.25. Okay. Okay, so generally, if you give me a probability of a signal, let's say for example, A, you tell me that this signal has a probability of, let's say, a 0.25, then I'd say, okay, well, this is the probability of A. Then I'd say, well, then alpha of A equals the probability of A, 0.25, times the probability of 1 minus probability of A, which is 0.75. Well, this ends up being 3 over 16, okay, if I got my numbers right. Okay, so here is, so now here for the inputs, we calculate the probabilities, or we are given the probabilities, and so we calculate the activities. How about the output? Well, for the output, every type of gate has a switching probability that we can derive the output probability based on the input probability. So for the NAND gate, for instance, the NAND gate says that the probability of the output equals 1 minus the probability of A times the probability of B. Typically, these are pre-calculated for you. For their derivation, you can consult one of those textbook on probabilities and statistics, or the LSI textbook, which goes deep into this subtopic. And but we'll take these as already calculated for us. So if I go back to the lecture here, and we can see that here in this table he has given these probabilities of the output of the gate for every type of gate, for AND2, for AND3, and some of them they make sense, but you can conclude them very quickly, for OR2, for NAND2, for NOR2, for XOR2. Okay, so here's an example. Suppose, for instance, we know that the probability of the input gates over here, okay, is 0.5. And we know what we want is to calculate the activity factor. Okay, and keep in mind, we want to calculate the activity factor for this Y. Again, the activity factor is important for us because it relates to power. That's why we are talking about activity factors here. Okay, so in terms of the probabilities that are given, I can from them calculate the probability of the output from this below table, which is, this is an AND2, this is an AND2. Here is the NAND2, okay, where it says that you subtract 1 minus the probability of the two inputs. So let's calculate the probability of this output. It is 1 minus the probability of A is half, times the probability of B is half. 1 minus 1 over 4, that gives me 3/4, and that is the number right here. And then we can compute the alpha here of course, this is for now node N1. So we can compute alpha alpha for N1 equals the probability of N times 1 minus the probability of N, okay, which is equal to 3/4 times 1/4, and that is equal 3 to 16, and that's what we got right here. Okay, so now we need to compute the probability of the output. So well, the activity of the output. So we compute, by the way, we compute N2 similar to N1. Now, the activity for the output is computed as follows. So we have, this is an AND gate. Similarly, I use this equation here to compute this probability. I have computed the probability of the inputs, and then I can compute the activity of the output based on the probability of the inputs. All right, so what? Now I computed the activities of all the nodes of the design. So what? Well, the activities should point out to me when I do power analysis, where are those nodes that consume most of the power, and typically they are the most active nodes. And the most active nodes are the ones that I need to study though and examine them and think about how I can make those nodes quieter if I could. And there are techniques to make those nodes quieter. For instance, okay, let's go. Whoops, going backward here. So for example, I could disable the clock for this. So what is this business of disabling the clock? Well, suppose for example I did my analysis and I found out that these nodes have very high activity. Then I trace them back to the bunch of registers that are active all the time. Now, I notice that those registers are active when they are needed and they are active when they are not needed. So, for instance, let's suppose, for example, these registers are feeding a floating point unit where it computes floating point math. Well, suppose I notice that these registers are active when I'm doing in my CPU integer execution. So those floating points, this floating point is active unnecessarily. So what do I need to do? Well, to make it quiet, what I have to do is to keep those registers unchanged, keep them not switching, keep them quiet. How? Well, this is called a trick called gate clock gator or killing the clock in some of their terms. And basically what we do is we disable the clock that goes into this register when we don't need the output of this register. Now, if we don't switch it, then he is quiet, okay, and the circuit here that feeds will be less active, and that result in smaller activity factor, which result in power. See the series of events now? So basically what we are concerned about is power. So we need to reduce power, and then that makes us reduce activity, and that makes us make those nodes quiet, and that makes us kill the clock when it is not needed. So we kill the clock when it is not needed by the clock gating. Now, there's an interesting thing here, though, is that how do we create this, excuse me, how do we create this enabled signal right here? Okay, so the enable latch here is an extra circuit that needs to be switching and burn power, which is kind of interesting. We wanted to reduce power, but we ended up creating extra circuit, which will um, add more area and more power. Well, that's why you have to do these things very, very carefully. And if this unit that you are trying to keep quiet is small and it is active most of the time, then probably creating such a overhead is not worth it. However, if this unit here is a large unit and it is not active most of the time, then creating this extra overhead probably would make sense, and you will overall reduce power. Okay, now so we say power is alpha, that's dynamic or switching, alpha CV square F. So we talked about things how to reduce alpha. How about reducing capacitance? Well, that's how we reduce capacitance by really making gates smaller, using few of them, okay? Reduce the interconnects, which reduces the wire capacitance. You have to do better floor planning. You have to you have to make sure that you really drive those long wires with a lot of care and optimum number of buffers and inverters. Okay, so this is we'll discuss this at some point in the class where we when we talk about when we talk about wires, specifically this point here. Now, how about the V? Well, in terms of the voltage and frequency, some um, so again, let's remind ourselves what we're trying to do here. Switching power equal activity factor C V square. Okay, so we need to reduce the frequency. Many of the um, microprocessors and chips nowadays, they have multiple frequencies. They dial down the frequency when they want to reduce power, or when they want to run into a lower, less efficient mode. And that ends up being, as you can see, less frequency ends up being less power. Another thing is to use, for V square here, is to use multiple voltage islands. And multiple voltage islands means that you have different voltages for the design, where for instance, in your design you have circuits that works off 1 volt and circuits that works on zero point 0.8 volt. Now, the 1 volt, typically these are the fast circuits, and 0.8 volt, typically the slower circuits, but you can afford having lower voltage. The problem is that when you interface these circuits with each other, then you end up having to implement something called level converter, where you interfacing from a certain level of voltage to another level of voltage. So they are certainly required when you are going from a low to high VDD. So if you have a signal from the zero point 0.8 to the 1 volt region, you need to implement such a circuit for converting the okay. And I'm going to stop here, and we will continue the discussion of this in the next class. Thank you very much.